Okay, hello everybody. Let us start the last lecture. Basically, it is not very much related to the previous one. I mean, that's another application of stochastic calculus that we developed. And I think it's going to be longer than just 2 by 45 minutes. So let's start. I mean, there are two stories for today. Again, somehow related, but can be considered more or less separately. And the plan is just to finish the first story before the break, whatever time it takes. So probably it's more than 45 minutes, and then discuss the second after the break. So this is another paragraph. Let us call it basic notions in stochastic differential equations. I'm not going to prove any serious result here. So basically, this is more like an account of what is going around with some examples. Just you are not frightened if you see, some SDE later on. Okay, so mostly it's going to be just a discussion of what are the notions and what are general results. So the first part is terminology. So what is a stochastic differential equation? Assume we have it's rather long definition. Well, assume we have, and it's going to be not a single equation, but a system of equations, or just a single equation in a matrix form. So assume we have two dimensions, d and m, and there are two functions, sigma and b, defined. The first argument is going to be time, so this is just r plus, and the second argument is space. So sigma is matrix valued. It's either m times d or other way around, depending on the notation. So in my notes, it's d times m, and this is vector valued. Okay. What I would like to do is to consider stochastic differential equations, or a system of which I'm going to write in a differential form. So this is dxt sigma t xt dbt plus b dt. So this is vector valued in Rm, and hopefully dimensions match. So what's that? By definition, it consists of, first, we should have some probability space. So some probability space. Second, we should have a collection of Brownian motions defined on them. So, and let me also add here and complete sigma complete filtration. Ft. Complete, as usual, means that it's right continuous and all the events of outer P measure 0 are in F node. Okay, then I need to have a realization of the Brownian motion, okay? Which should be d-dimensional. motion dt. Again, I'm writing it on the whole half plane, but you can restrict yourself to 0t. It's not a big issue. D-dimensional Brownian motion started from 0. And then an adapted process adapted to ft. Process xt such that xt is x plus stochastic integral of that plus still ts integral of this. And this, of course, should be understood component-wise. This is vector valued guy, so okay, you can think about a collection of equations. So here is the definition. Well, it looks rather reasonable. I mean, what else can we declare to be a solution, a solution of that? But there are some issues. So an important remark is that, in the very center of the blackboard, we do not fix neither the probability space nor the realization of the Brownian motion. So we saw in last lectures and in exercises that there are several Brownian motions defined on this, adapted to the same filtration, right? So if there is a Brownian motion B, you can construct another one which is also adapted to this filtration, and in principle you can continue. So we do not fix anything here. I mean, this is just a Brownian motion. Do not fix neither omega nor beta in this definition. Okay, so now another set of definitions. This SDE, let me denote it somehow, like star. So it should be some terminology about existence and uniqueness. Okay. Weak uniqueness if for any, I didn't say anything about x, x is just a point, starting point in RD. Okay. Weak uniqueness if for any x there exists such, such a bunch of objects. Exists omega motion xt such that this holds. I mean, if you can invent somewhere on the Mars, so whatever, somewhere in the outer space, the probability space, filtration, Brownian motion, and such a process. Yeah. Then, oh, this is weak existence, sorry. Weak existence. It was strange, yeah.
Which conditions do we fix on the sigma and d?
Right now, only measurability. Then there's the question, what is enough to guarantee these properties, and this is a subject to discuss. So that's a good question. Right now, they are just measurable. I mean, to be all these things well defined. I mean, then there's the question, okay, if you are able to define the stochastic integral or not, and so on and so forth. But in general, just measurability. Measurable. Then weak uniqueness. If all solutions I mean, all such solutions started from the same x actually are the same in low. If for any x and for any x1, we define them this way, solutions defined on different probability space. We have xt is the same as x tilde in low. Okay, which basically means if I construct a solution here on this blackboard and you do another construction on that blackboard, then the law of the result is the same. Okay. But this is a bit non-constructive, so this is exactly the reason for the notion of weakness, of weak existence and weak uniqueness. Why? Because you can think, okay, let somebody gives us a realization, I mean a realization of Brownian motion, something very, very concrete. And then we can ask, okay, in this particular probability space, if these two guys, I mean, I still can speak about weak uniqueness, but if they're just the same in distributions or exactly the same, okay? So this is called pathwise uniqueness. If for any realization of the Brownian motion, these two processes basically just coincide. So if for any realization and for any xt bar, okay, again with the same x, and now they solve in the same probe space. And for the same BM. So if, okay, we have that x and x tilde are basically the same process, up to possibly events of zero probability. Okay. And then there is the last notion here on this blackboard. X is called a strong solution. If it is adapted to the complete filtration generated by the Brownian motion itself. Note that here I didn't ask that Ft has something to do with Bt. Bt is adapted to Ft, but in principle Ft can be larger. I mean, it might contain some information, some more information. Okay, so basically what is the reason for the last notion? Just imagine that you would like to solve, say, such SDEs numerically. Then the very natural way to proceed is just a sample Brownian motion, however you represent it in a machine. So you just have some sample, and then you say, okay, let me define xt in some way, starting with this particular sample. But then it's good to know that you have pathwise uniqueness, that you do not lose anything. I mean, that everything is actually determined by Bt. And we will have an example just in a minute. there is a general theorem, which I think is good to formulate right now. And general theorem is that if there is weak existence and pathwise uniqueness, then, okay, the life is nice. We have, in particular, weak uniqueness, and meaning that all of them have the same, the same distribution, whatever probability space you consider. I mean, this is not trivial. So pathwise uniqueness is a property that says something in a given probability space. And weak uniqueness says something about the law, right? So these are different properties. But the theorem actually guarantees that this is the key property. Uniqueness. And moreover, in this situation, all the solutions are actually strong solutions. Okay. Yet again, let me insist on the fact that in principle, it is not clear why this is a stronger property compared to that. Okay, so why, if we have this pathwise uniqueness on this blackboard, and you also have another pathwise uniqueness on your board, why we should obtain the same distribution? Okay, but that's good. Okay, and now just to illustrate what is the difference between two properties, just an example why this is not the case in the other direction. So let's remark. And in fact, we already saw this example. I mean, let us consider the stochastic differential equation. Of this form. Sine c dbt. Just in 1D. And this function is either plus or minus 1. I do not admit sine to be equal 0. Then the first claim is that we have this uniqueness in law. Okay? We have weak uniqueness. Why? Just by Levy theorem. Levy characterization. Because if it solves this SDE, then okay, xt is a local martingale with quadratic variation, just sine squared quadratic variation b just okay. So this is a local martingale, and x squared minus t is also a local martingale. So we know that it's distributed again is a one-dimensional Brownian function. Okay? But on the other hand, we do not have pathwise. Why? Just note that if, say, beta t I constructed, nope, what should I say here? Yes, let us just construct this beta t. BS, thanks. So we saw that this is again a Brownian motion. And note that, okay, now if I rewrite this stochastic integration, then what I know is that, and multiply by the sign with the other side. So what I know is that dBt is sine bt d beta t, right? I just use that sign is either plus or minus 1. So in particular, it means that bt solves this stochastic differential equation with the underlying Brownian motion beta. Okay. There is some mess because, okay, here it was B, but remember that in the definition of solution, I'm allowed to take whatever Brownian motion I wish. In particular, I can take this one. Okay? At the same time, if I started, say, started at x0. At the same time, minus bt also solves. That's just not completely trivial, because I should say something about the zero set of the Brownian motion here. Basically, I should say that it doesn't matter if I put greater or equal here or less or equal there. But we already had this discussion. That's exactly what happened maybe last time. Okay, so you see, now there are two solutions. Everything is defined exactly on the same probability space. I have two Brownian motions, B and beta, defined there. Now I consider beta as being given, okay? And now I see that, okay, there are two solutions. They have exactly the same law, but why is they different? And moreover, it was in their exercises, in fact, this is not a strong solution. Okay, because we know that sigma algebra generated by B is strictly greater than the sigma algebra generated by beta. Okay? That not solutions. Just to illustrate it yet again, a bit better, let me just comment that actually there are much many solutions. All them defined on the same probability space. Actually, you can take for any stop in time, you can let us consider another stop in time. Let me denote it maybe this way, or maybe let it be sigma. I put here sigma. That's a very local notation. It's not going for long. So which is just the first hit to 0 after tau. So here was my Brownian motion running, and here it was whatever, say first hit of 1, which was sigma, and this is tau not sigma. Okay? Then the process xt, which is bt for t less than tau and minus bt. Tau not sigma. Tau not sigma. Pardon? This is sigma, yes. It was redefined on the fly. So what I'm doing, I just fix some moment, maybe even deterministic. I take the first hit to 0 after that. And then what I claim is that we have two options how to continue after that. This is a bad picture because right after there is also an infinite number of crossings. But anyway, there is this trajectory and the opposite trajectory. So loosely speaking, each time you hit the 0 level, you have a choice how to continue. This is more complicated because the 0 set of the Brownian motion is contour type set. But okay, say for first hits of the level 0, you definitely can do so. Okay, and this exactly illustrates what is the notion of the strong solution. The strong solution, loosely speaking, again, it says that we do not need any additional information to find x. And here we use some additional information each time. Okay. Are there any questions so far? Well, if not, then some general existence theorems and some discussion of Bessel processes, which you already had in exercises. Let it be. General existence and uniqueness theorems. The parallel you should have in mind is, of course, ordinary differential equations. Okay, so there is somehow similar but simpler theory for ordinary differential equations, and what we should expect is that if the coefficients are nice, then the solution is exists and is unique. So the very first theorem is exactly claiming exactly this. So this is Lipschitz case. Well, if both coefficients are Lipschitz, in the space variable, then everything's okay. Then vice weak existence and pathwise uniqueness. And as a consequence, everything else. So this is a nice case. And again, yeah, and I didn't say, sorry for this, I didn't say what is the dependence on t, on the time. And in time, just continuous functions. If it was d or m, I don't remember, it was d. A small remark. First is that, Okay, this is of course very similar to ODEs. And second is that, in principle, if you wish, you can ask for this condition only on compacts when x and y are on some compacts. So one can replace by ck for xy on a compact set. But still, you must have no more than linear growth in infinity, provided still they are not very large at infinity. And this is again very similar to ODEs if you think what conditions for ODEs guarantee you that solution exists for forever, that it does not blow up in a finite time. Well, basically this is the same condition. So you should not expect, in particular for B, I mean, you should not expect that you can gain something. Okay? So what are the examples? Erase all that. Sure, there are many examples. The goal for today is just discuss Bessel processes because it might be helpful for other courses. And in fact, this is, the very basic example. But the first example is simpler. Let me just think about the stochastic differential equation of this form. Well, this is a Lipschitz function of x. It fits. So we know what the solution is. This is the exponential martingale, right? Somehow this is the most trivial example you can think about. I mean, the most interest is, of course, in the coefficient in front of b, of db. Otherwise, dt, I mean, if it was single dt, this is just ordinary differential equation. And this is the simplest Lipschitz function, which is just x. Okay, and then let me write definition of the Bessel processes. We have some troubles here, right? Because the function is not even bounded. I mean, this 1 over x. M will be at least 2. Not necessarily integer. Okay, to make it somehow better, let us consider the first moment. I mean, let us slightly modify this equation. I mean, to fit in the conditions of the theorem. So let me replace this function by just this provided xt is at least delta, 0 otherwise. Maybe this is still not very good because this is not continuous. Okay, if you would like to see a continuous function, just some continuation, I mean, between delta 2 element, if you would like to make it a nice function. Okay? Then, just a comment. Up to time tau delta, which is by definition the first time we hit delta, and x is going to be positive. Up to this time, nothing changes, right? This is exactly the same equation. Right. And now let us make a simple computation. Just here, imagine that we would like to find some martingale of the form f of xt. For a smooth f, what is df xt? This is just theta calculus, nothing complicated. So stdb plus f prime over 2 plus m minus 1 over 2 st f prime st dt. Right? I mean, this and that come from the first term. This is just the x, and this is the quadratic variation term. Okay? So if f is what? Hopefully, it should be x 2 minus m. Then the first derivative is 1 minus m, and it cancels here eventually, or log for m2. Then this cancels. And we have a local martingale. So this xt 2 minus m is a local martingale. Moreover, so it's uniformly bounded, right? Because everything what's going on to happen happens before time tau delta. And then, okay, if I put here, say tau delta is a true martingale, just because it's uniformly bounded. Okay? So it can be, x cannot be now too small, and the power is negative. Is a martingale, and just by optional stopping, you say, okay, the expectation of what? Of the probability of the event that we actually stop at the level delta. So the picture is that we start here, then we either stop at the level delta or continue up to time t. The probability of this event cannot exceed, I mean, such an event contributes delta to minus 2 by x naught to minus 2. What I'm saying, I'm just saying that if I'm not messing things up, I'm just saying that, okay, the expectation of, since the expectation of x tau delta 2 minus m is x naught 2 minus m, and it is at least delta minus m, this probability. If it's the same, yes, it is the same. Is it clear, I mean, what happened? You may think about just computations for integers m. And then for if m is integer, then x2 minus m is exactly what appeared in exercises. Okay, so in particular, it means that if I now pass to the limit when delta tends to 0, then the probability of this event is small. In particular, probability of that tends to 0 is delta tends to 0. Which actually means that again you can first define this process using this modification of the drift term, and then say, in fact, if I pass to the limit when delta tends to 0, then I can just remove all the modifications here. Yeah. And remove the cutoff. The definition of and just think about it as it was written. Yeah. What we proved along the way is that if we take Bessel process of dimension at least 2, then it does not hit the 0 level, never. So we perfectly know this for integer dimensions, because if m is integer, then xt is nothing but the absolute value of the m-dimensional Brownian motion, and the m-dimensional Brownian motion doesn't hit the origin. But this is exactly the same proof, even if m is non-integer. Okay, and then there is another case. So this Lipschitz existence and uniqueness theorem, I mean existence and uniqueness in the Lipschitz case, it works in any dimension, but actually in dimension 1 the life is nicer. The reason is that in dimension 1 there is another tool available, like comparison of two solutions. There are local times, which is a very powerful tool. And actually in dimension 1, okay, now 1D case is sigma 1/2 period. In this case, in 1D, if you have you can weaken the conditions. So if you know that sigma tx minus sigma ty is less than some constant square here, it's minus y, you know, yes, minus sy is still Lipschitz, and this is for any xy and for any s less than t. I do not assume any continuity in time now. I mean, what I assume is that they are Lipschitz, and yes, and also I assume that they are bounded in time in the first variable. So if I have all that, then otherwise uniqueness. So again, let me insist that this is the crucial property for SDEs. I mean, if it holds, then solutions are strong, if they exist, etc., and so forth. Okay. The message is that here you can relax to Hölder 1/2. This is the message. And okay, let us just consider the single example, which is again basically the Bessel process, but now the squared Bessel process. Again, it already appeared in exercises. So example. T with M0. Well, square root of xt, maybe it's not very well defined. Let us put absolute value here for a moment. Maybe in some different color. Okay. This exactly fits this theorem. Okay. So what we know is that, oh, yeah. Sorry for this. Sorry, guys. Yeah, I forgot to tell you another important fact. Moreover, in this setup, similarly to ordinary differential equations, you are able to compare solutions. So in ordinary differential equations, you know that if, say, for a given equation you started above, I mean the first solution started above the second, then it remains above. Okay, this is the comparison theorem. And the same happens here. So moreover, if B1 is greater than B2 and X1 is greater or equal than X2, and xt1, xt2 are defined on the same omega with the same Brownian motion, then the solution stays above. This is x small, this is x capital. Then the solution stays above for forever. Okay, this is similar to ODs.
There's no conditions on sigma.
And sigma is the same. I mean, let me put it here to be clear. Yeah, sure. Otherwise it would be strange, right? I mean, if I just take two different sigmas, I mean, even without, if I just take two different constants, like dxt is dbt or 2dbt, these are two Brownian motions with different variances, and they behave in a quite chaotic way. So thanks for asking. It's implicitly assumed that sigmas are the same. So, so basically this story and what's going to be next after the break is more like a story about, you know, some nice coefficient here, maybe, and some additional drifts. Okay, here in this example, if we do not think about existence of such processes, I'm going to comment in a minute. What we know that, okay, we have these strong solutions, and by comparison theorem, so we know that if we start at some positive point, then let it be x1, then it remains greater than x2, where x2 is started just from 0. Okay, let us just consider two solutions. The first started here, and it evolves in some way. And the second is just started there. And for the solution started at 0, it's easy to guess how it behaves. Okay, we know that 0 solves it. I mean, if this is 0, okay, everything. What do I say? Okay, this is with B1 being M, and this is with B2 being 0 as well. Okay. What I know here is that I have a freedom to to push B lower, and my solution is still measure-rated. Okay. So if I just consider B1 being a constant M and B2 being a constant 0, then in the second case, it's very easy to guess what X is. So this is just a constant. And what we know is that, okay, then xt1, which is exactly what we need, remains non-negative. So we can write square root of xt instead of okay, so the message here is that if I raise this absolute value, this is still a properly defined SDE, and it has some solutions. Okay. Now, two last remarks for the first part. So remarks to this example. The first remark is, okay, how it goes with general existence theorems. Here I actually put something on the carpet. I said, okay, there is a pathwise, there is weak existence. Oh, this is another, yeah. I mean, it was really behind the blackboard, so under the carpet. So I said it's pathwise uniqueness, but I didn't say anything about existence. So the general theorem about weak existence, as far as I understand, is the following. So if you have just bounded, for instance, sigma and b, and you know that sigma is also bounded away from 0, that absolute value of sigma is greater than 1 over 100, greater than epsilon, then there is weak uniqueness. It's a bit shame, but I don't know if there is a really general result. I mean, for sigmas that might vanish. Maybe there is. So please read Revos-Yor or other monograph on that. I didn't find the answer there, but yeah, maybe I'm just bad. Okay, so in principle, it might be some issue here to prove ST exists. One can just use the construction from the previous example. So you just construct Bessel process as a solution to the previous example and stop it when it hits 0. One can use previous construction, and take a square. This is about the computations that were in the exercises sheet. So what is the picture? What is the picture for m less than 2? We have some process, then we will see that with positive probability it hits 0, and then I just define it to be 0. Okay. What I'm saying is that, okay, this gives me a solution. This is exactly how they behave. Okay. Remark B, that I have no place on the blackboard to write it, so okay, let me try to make it here. Anyway, it's erased after the break. Remark B is that thinking about ODEs, one might expect that, okay, even two remarks. So the first remark is that for ODEs, this condition, I mean the condition that coefficients are only Hölder, is not strong enough to guarantee uniqueness of solutions. So you know, if you consider an equation like f prime is square root of f, and that's it, then it has not a unique solution. You may stay at 0 for a while, and then at arbitrary moments start growing. So here, okay, this is another coefficient, of course, this is sigma, not b, but the condition is weaker. And again, in parallel with ODEs, one might expect that if, say, here you have a strict inequality, then the first solution stays strictly above for forever. So, remark, it is not true. And to understand what's going on, just think about this example of Bessel processes. So here is basically how the solutions behave. So for m less than 2, you start somewhere, you evolve for a time, then you hit 0 and you stay at 0 for forever. So this is the solution. If you start, it's going to be impressionistic. If you start above, then you know that you stay above. In general, again, you hit 0 at some point, and then you collide with all the other solutions. So, I mean, the picture of different solutions is like this, or like that, etc. So, okay. What happened? I mean, what's the bottom line of the first half? There is some general theory, so not be very frightening if you see some SDEs. And there are some simple facts about Bessel processes. Okay, maybe the most important fact is the important knowledge is that they are well defined. The squared Bessel process is defined for all non-negative exponents. The Bessel process itself is not well defined if dimension is less than 2. So the reason is basically exactly here. So you need to do something with zeros. And here is the very simple computation why there is such a threshold at m equals to 2. Okay. Good. Now let us make a break, say for 15 minutes. And after the break, it's going to be another quite important thing for understanding at least one of the next courses. It's not long, but just stay here, please.